So in this lesson, we're going to take a look at a specific kind of probability distribution called the binomial distribution. And by the end of this lesson, you should be able to use the binomial expansion that we've looked at before to determine the probabilities of outcomes in a binomial experiment. Now, before we can do that, we're going to have to talk about what exactly we mean by a binomial experiment. And a binomial experiment has certain conditions that need to be satisfied in order for us to be able to use the binomial expansion to calculate our probabilities. So first off, the conditions for a binomial experiment. In a binomial experiment, you are always doing repeated identical trials. You are doing something over and over and over again, and you're doing the exact same thing every single time. Okay? There are only two possible outcomes in each one of these trials. Okay? And we usually call one of these trials success and one of them failure. Those are just the names that we use. The probability of success does not change from trial to trial. Okay? Otherwise, if it did, they wouldn't be identical trials. But the probability has to remain constant. Okay? And what we are doing in our experiment is we are counting the number of times we get this thing that we have called success. Okay? So a classic example of a binomial experiment is tossing a coin over and over and over again. There are repeated identical trials. Each toss of the coin is exactly the same. There are only two possible outcomes, heads or tails. And if our experiment involves counting the number of heads, we'll say, okay, each time we get a head, we'll call that a success. Each time we get tails, we'll call that failure. And as long as we don't change the coin, the probability of getting heads isn't going to change from one trial to the next. So it meets all of these conditions for a binomial experiment. So in a binomial experiment, there are four variables that we're going to be interested in. We use the variable n to denote the number of trials. So how many times we are repeating each trial in our experiment. We use p to represent the probability of a success. However, we have defined success, whichever outcome we consider to be success. We use Q to represent the probability of failure. But because there are only two outcomes, success or failure, in a binomial experiment, Q is always equal to 1 minus p, okay? Because the probabilities have to add up to 1. And finally, the whole point of our experiment is to count the number of successes, so we use the variable k to represent the number of successes that we are interested in. So let's look at an example here. A multiple choice test has 5 questions, each with options A to D. What is the probability of getting 3 questions right just by guessing randomly? What should we define as being a success in this experiment? Well, first off, is it a binomial experiment? We have repeated trials, so each question on our test is considered to be a trial. There are 2 possible outcomes here. We can either get the question right or we can get the question wrong. Does the probability of success change from question to question? If we're guessing completely randomly, then no, it doesn't. And we are interested in counting how many questions you get right. That's what they're asking us in this question. So what should we define as being a success in each trial here? Getting a question right. So let's say question right equals success in this case. Now let's try to figure out what are the values for each of these 4 variables, n, p, q, and k. N is our number of trials, so how many trials are we doing here? We're doing 5 trials. Absolutely. What is the probability of getting a success in one of these trials? 1 in 4. Assuming you're guessing completely randomly, each multiple choice question has 4 options. Once we know P, we know Q. Q is going to be 1 minus 1 over 4, so it's going to be 3 over 4. K is the number of successes. So in the question, how many successes are we trying to find the probability of? 3. So let's look at how we could maybe use the probability we've done up till now to try to answer this question. So we want to find the probability that our discrete random variable x is going to take on the value of 3. If you were to just if I had just asked you to do this question on an assignment, you might think, well, let's list all the possible ways I could get 3 questions right. I could get the first 3 correct, so I'll use CCC to represent the first 3 being correct, and then maybe I could get the next 2 wrong. And I could work out the probability of that happening. And then I could add it to the probability of, let's say, getting the first one correct, the second one wrong, and then the next one correct, the next one correct, the next one wrong, and so on and so on. And I could add this to this. I could add the probability of, well, so on and so on and so on. You could think of all the possible ways you could get 3 correct and 2 wrong, and then calculate each probability. But let's just take a look at one possible arrangement or ordering of these correct answers. We know that the probability of getting this one correct is going to be 1/4. Okay? The probability of the next one correct is 1/4. The third one correct is going to be 1/4. And then the probability of getting the next one wrong is 3/4. And the probability of getting the last one wrong is 3/4. So if we wanted to find the probability of getting the first 3 correct and then the last 2 wrong, this would be the probability. Now, each one of these other probabilities that we're going to work out is going to have the same, it's going to have 3 3/4 in it, and it's going to, 3/4 in it and 2 3/4, because no matter how we get the questions right or wrong, we're going to have 3 of them right and 2 of them wrong. So what we can rewrite this as, well, let me stay consistent in my color here. I'll say the probability that x equals 3. We know that no matter what happens, we are going to have 1/4, a 1/4, a 1/4, a 3/4, and a 3/4. And all we have to figure out is how many ways can we rearrange these right answers and these wrong answers to get our very different possibilities. Okay? So we'll always have 3 right and 2 wrong. So how many ways can we rearrange these 5 things if we have 3 identical things here and 2 identical things here? Those possibilities can just be represented by a combination. 5 choose 3. So the probability here is going to be 5 choose 3, 1/4 cubed, 3/4 squared. Now, what is important about these numbers that I've got here? Well, 5 choose 3 is n choose k. Okay? N was our number of trials, k is the number of successes. 1/4 was our value for p, 3 was our value for k, 3/4 was our value for q, and 2 is our value of n minus our value of k. So this expression should look reasonably familiar. Okay? This is just the binomial expansion where we have put in p and q instead of x and a when we were doing it before. So to finish this question off, we could work out what this number works out to. It works out to be something like 0.0878, which is approximately equal to 8.8%. And the little equal sign with the dot over means approximately, just to indicate that I've rounded that off. So the big thing here is this, okay? This is sort of the definition of the binomial distribution. The probability of k successes in n repeated trials, if you are doing a binomial experiment, is the probability that our discrete random variable x will take on some value given by k, is n choose k, p to the k, q to the n minus k, okay? Where p is the probability of success and q is the probability of failure, or 1 minus p. And if we're using the binomial, if we're doing a binomial experiment, the expected value is particularly easy to calculate. It's just the number of trials times the probability of success. Okay. When do we use the binomial distribution? If we are choosing things from a population with replacement. So if you can imagine an experiment where we are pulling cards out of a deck of cards, as long as we're putting them back in again, we can use the binomial, we can treat it as a binomial experiment because the probabilities aren't changing from trial to trial. It is sometimes used when we are not doing replacement if the probability, if the population is very large. If the population is very large, we can assume that the probability doesn't change very much from trial to trial, even though we're not doing replacement. Okay. So let's apply this binomial expansion here to a couple of questions here. So let's go back to our multiple choice test. It has 5 questions. Each has options A to D. If we are, again, guessing randomly on each one of these questions, what are your chances of passing the quiz? And then what is your likely mark on the quiz? So if they're asking us, what are the chances of passing the quiz, what possible marks can we get that are going to let us pass this quiz if it's out of 5? What do you think, Cheyenne? At least 3 of them right. So we can get 3, we can get 4, we can get 5. So we are interested here in the probability that our random variable x will take on values greater than or equal to 3. In other words, we want the probability of getting 3 questions right plus the probability of getting 4 questions right plus the probability of getting 5 questions right. What is the probability of getting 3 questions right? Well, we actually already did that one. We know that it was 5 choose 3 times 1/4 to the power of 3, 3/4 to the power of 2 from the previous question. If we want the probability of getting 4 correct, 5 choose 4. Our probability P, I should put in 1/4 there, to the power of 4, 3/4 to the power of 1, because we're only getting 1 question wrong. And then finally, to this we want to add the probability of getting 5 correct. So that's going to be 5 choose 5, 1/4 to the 5, and then 3/4 to the 0, which will just be 1. So at this point, it's just calculator work. You got the combination, and you put the values into your calculator. So our first term here, we would get something like 0.08789. Saw that number before. Our probability of getting 4 of them correct, 0.01465. Our probability of getting 5 of them correct, 0.0098. Now, we might want to pause as we're doing the question right here and just make sure that these individual probabilities make sense. This is suggesting that it's more likely for me to get 3 correct than it is for me to get 4 correct than it is for me to get 5 correct. So my probabilities are decreasing each time. Does this make sense? Yeah, it does. We're actually quite unlikely to get all of these things absolutely correct. So we could go ahead and we can add them all up. 0.10352, which is approximately equal to 10.4%. So 5-mark quiz, 4 choices, randomly guess on each question, chances that you're going to pass, about 10%. What is your likely mark? Well, what they're asking us to calculate here is the expected value, or the expectation value, for your mark on this quiz, which is just n times p, or the number of trials, times the probability of success. So the number of trials here is 5. Our probability of success is 1/4. So 1.25. So that would be a mark out of 5. Now, you can't actually get 1.25 as your mark on the test, but if you did this over and over again, that's what you would expect to get on average. Okay. So let's do one last example here, and then I'll save my big example for the next lesson. What is the probability of having at least one boy in a family of 3 children? Okay. First off, is this a binomial experiment? Sort of the meta answer is yes, because why would I be talking about it today if it wasn't? But does it meet the criteria for being a binomial experiment? What do we think of? What can we think of as one trial in this experiment? Each child is a trial. Are there 2 possible outcomes for this trial? Hunter's nodding. He says, yeah, you can be a boy or a girl. Now, there are other possibilities, but let's just assume straightforward boy and girl here. Does the probability change from trial to trial? No, it's going to stay constant at 50%. And are we interested in the number of successes? Okay. Yeah, we are. We're interested in the probability of having at least one boy. Okay, so we're counting. It looks like what we're going to say is that um, if it's a boy, it's a success. If it's a girl, we'll count that as a failure, and we'll count the number of successes here. However, this question is actually easier to do if we use an indirect method. The probability of having one boy is, of course, 1 minus the probability of, oh, sorry, I should say one boy. I should say at least one boy. Is 1 minus the probability of having no boys. Because if you don't have at least one, then you have none. So having no boys is the complement of having at least one. So really this is 1 minus the probability of having 3 girls. So to do this experiment, we will say having a girl is a success. Okay. And if we say that, we can work out this probability here of getting 3 successes, and then do 1 minus that probability to get the answer that we are actually trying to get. So we need to identify N, P, Q, and K. How many trials are we doing? We are doing, well, we have 3 children, 3 trials. What is the probability of a success? Well, we'll say that's 1/2. 50% of the time you have a girl, 50% you have a boy. It's not exactly 50%. I think it's something like 51%, but we'll just go with 1/2. Q is 1/2 as well. And we are interested in the probability of 3 girls, so the number of successes we're trying to find is 3. So let's work out the probability of 3 girls. Our binomial expansion here is going to give us 3, choose 3, 1/2 to the 3, and then 1/2 to the 0. We can work this out, 0.125. So that's the probability of having 3 girls. So the probability we're really trying to find, probability of at least 1 boy, is going to be 1 minus 0.125, or 0.875. Okay, or 87.5%. So if you're having a family and you have 3 children, there's an 87.5% chance that at least one of those 3 children is going to be a boy.